Hello and welcome to my new video. This time, as in the last one, it is again about leaves. And this time I will do something a bit more complex than the simple petal for my last video. I will go for a beech leaf. At the very start, I decided I had to use a simpler approach than for the petals. So I decided to build my flat blobs no more from flat discs, where it is necessary to orient them according to the normals, but to use simple spheres instead. So no more need to look at normals anymore. In return, I now have to use more elements for building up a given structure. As a plus side, on the other hand, with relatively small spheres, I am now producing smooth edges. So no need for cutting these edges. Anyway, let me show you my approach. In short, I'm using splines for building up a given structure and for directing the sheets connecting these splines. In the case of my beech leaf, I'm starting with a simple approach by just using 3 splines for defining the whole leaf. Spline 2 refers to the main vein of the leaf. The other 2 splines refer to the left and right edge of the leaf. When trying to connect spline 2 with either spline 1 and 3, it is important to start with corresponding positions on each spline. I am creating such corresponding positions by starting with the leaf axis and positions evenly distributed along this axis. In reality, I have been using many more positions than only these few, of course. This here is only for demonstration. For each of these positions on the leaf axis, I am looking for orthogonal projections onto the various splines. This may appear somewhat exaggerated, since the leaf axis is parallel to one axis of the coordinate system. I also could look for positions on the splines with identical value for the respective coordinate, but I wanted to develop an approach applicable somewhat more in general. How do I find orthogonal projections P1, P2, and P3 of our initial position P0 on the leaf axis? Let's have a look at 2 vectors. One of them representing the leaf axis, vector A, the other one connecting our point on the spline P1 with the position on the leaf axis P0. I have called this vector P in my figure. In the case of an orthogonal projection, vector A and P should be rotated by an angle of 90 degrees, which translates to a scalar product of the 2 angles of 0. For finding a position on spline 1 fulfilling this condition, I slowly migrated along the spline until subsequent scalar products no longer decreased in their absolute values. Then I had found the orthogonal projection of P0 on spline 1. I did this search for all positions on the main leaf axis and for all 3 splines, storing results in respective arrays. This way, I obtained sets of corresponding positions on all 3 splines. Now I only had to connect all corresponding positions by sets of small spheres, and my blade connecting, example given spline 1 and 2, was ready. Here you can see the results of this operation for the whole leaf. Script for this beech leaf are available as always on my GitHub account. This leaf can be further decorated by lateral leaf veins. A system of such veins can be defined as splines in a certain distance above the leaf. Subsequently, spheres set onto these splines are translated downwards until hitting the leaf. The result then looks like this. Nevertheless, I thought it might be possible to make the leaf look somewhat more natural by using lateral leaf veins as guidance for constructing the sheets. I started by adding lateral veins into this construct of main vein and leaf edges just presented. The main task was then to construct sheets between neighboring lateral veins. In this case, this task is relatively straightforward since the splines have a very similar structure. We simply use the same variable to obtain corresponding positions. For obtaining particularly natural leaf blades, I experimented with nonlinear connections between neighboring lateral veins. Let's take a look at this example with a sheet between the first and second lateral vein on the right-hand side of the leaf. When taking a look on the edge of this sheet, you can see that it connects the 2 veins by a straight line. We can change this by adding a quadratic equation to the y-coordinate of the spheres. Now we have a curved connection. For the final object, this curvature was still too much, and I rather used a very slight curvature as shown here. I used such a curvature also with respect to the x-coordinate. Since the leaf axis was located along the z-coordinate, this resulted in a slight indentation between the lateral veins. So there are only 2 things I still have to explain, the very bottom and the very top of the leaf. These were constructed on the one hand by a sheet between the outer edge and the first lateral vein, and on the other hand by a sheet between the main leaf vein and the outer edge. This was everything for today. Next time I will construct a few more leaves, so stay tuned.